All right, hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at theories of everything from the past, ancient and modern, and uh, delve into them deeply and try to show how they can help you in your life. They're paradigm shifting, you're awakening to 5D consciousness, you're forming a holistic worldview, and so on and so forth. Today is our 497th video that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an American engineer who lived in the 20th century. He was born in 1898 and died in 1990. And during his fairly long life, he put out a dozen or so books and many articles and talks and presentations. And in 1959, he articulated his two fundamental postulates about how he believed the universe operated. And then from there, he derived a theoretical universe, how his universe would look if his postulates were correct. And then he compared his theoretical universe with the actual universe, or so-called actual universe, of the mainstream legacy scientists that they have compiled in their scientific tables. He does that here in the book that we're looking at today, called Basic Properties of Matter, which is on chemistry. Larson arrives at equations for many of the basic properties of matter, like the melting point, or the interatomic distance, or the specific heat, the compressibility, and then he plugs in all the atoms and many molecules into his formulas, and then compares his results with the scientific tables. And I'm convinced that he's onto something, because he's able to more or less recreate the scientific tables strictly from his theory. No need for any type of, billion-dollar grant to have a laboratory and have armies of scientists to make these measurements. You can just get it right out of Larson's head. So that's compelling to me, and so that's why we're one of the reasons why we're delving in deeply into this. It also makes a lot of sense to me. Larson is one of the first people, not the first, but it's not very common. Rene Descartes and Thomas Hobbes had the same ideas, where they attempted to construct a universe based on motion, not matter, not energy, but motion. But Larson distinguished himself from them because he was able to, I guess the way he defined motion, he was able to turn it into an actual generalized theory that applies to everything. And I think he did that by defining motion. In particular, in his first postulate, he defines motion as the relationship between space and time. And he also defines motion, or at least points to a specific kind of motion that he's talking about, which is what he calls scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. So this is a motion that you can envision using a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other, and but they won't be moving in any specific direction. They'll either be moving in or out, or out. But if you reverse the balloon and contract the balloon, then they'll be moving in, and they'll be moving out away from each other, meaning that they're moving in all directions, or they'll be moving inward toward each other, meaning that they're moving inward in all directions. That outward movement, Larson refers to that as the progression, and the inward movement is analogous to gravitation. And so that kind of that transition, that progression, that is omnipresent, always existing. And that is the source for all manifestation. But that is really the empty universe. But the universe manifests by converting that outward progression to an inward motion, gravitation, which is inherent in all matter, all manifestation. So that just gives you a little bit of a glimpse of how the reciprocal system operates. But if you want any more detail about that, you probably want to watch one of my first 474 videos on this subject. I go into that in a little bit more detail and flesh out the fundamental postulates and what the ramifications are. But we want to try to turn some pages of this book today. And so I'm going to basically assume that you have some kind of background in the reciprocal system before we start here on chapter 16 of this book called Induction of Charges. I will recite the first postulate of Larson, which is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So the universe is made out of motion. Motion is the relation. It's talking about a scalar motion in particular. Motion is the relationship between space and time. Space and time are not existent in and of themselves. They only exist together in motion, and they have a reciprocal relationship in motion. And space, time, and motion come in 3 dimensions, and they come only in discrete units. And then he takes that first postulate and kind of plugs it into the second postulate, which is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And so he takes that, which is kind of the scientific consensus, and he derives his theoretical universe by, using the laws of probability and other laws of math and the laws of geometry and logic to arrive at this theoretical universe and his equations for these various basic properties of matter. Now, chapter 16 of this book is called Induction of Charges. And this is one of, I believe, about 6-7 chapters that Larson does having to do with electricity. And in my opinion, this is one of his weakest areas. I think he made a few mistakes in his derivations here, and so do some of Larson's other associates. And we will actually look at some of the dissenting voices as well here to kind of get a more balanced picture about the charge picture. But this is a weak point for Larson, and it is a weak point for me as well. I don't understand electric charges very well, or electric current, or anything. Larson's basic theory is that the electron is uncharged. I can accept all of this here. The electron is uncharged. It can take a charge. But like everything else in Larson's system, an electron is a kind of motion. An electron is a rotating unit of space. And it moves through matter in the same way that matter moves through space. Or really the reciprocal of matter moving through space is the electron, or really a whole, moving through time, which is matter. Matter is generally made out of time. and kind of like effervescence, kind of like a bubble moving through water, something to that effect. And that is the uncharged electron, and that is electric current. But static electricity is a charged electron. But a charge is not inherent to an electron. A charge can be taken by an electron, but a charge can also be taken by matter or submatter or subatoms. And charge is not an electron, which is kind of what is assumed. But the charge is, like everything else, a kind of motion. A charge is a rotational vibration. Which is kind of a motion like this, like the hairspring of a watch. And that is what gets applied to both, atoms, subatoms, and electrons. Okay, let's see where he goes here with this book, with this chapter, Induction of Charges. Clarification of the structure of the gravitational equation and application of the new information to the formulation of the primary force equation opens the door to an understanding of the Coulomb equation. F equals Q prime over D squared. That expresses the electrostatic force. And those Q's refer to charges. And although in the last chapter, Larson turned one of those two capital Q's into a lowercase q and changed the units. In Larson's system, all scientific phenomena come in units, and those units are time and space based exclusively. So where you have the MKS system, meters, kilograms, seconds. In Larson's system, you just have space and time. And so you have, for example, motion. The bike is going 10 miles per hour, 10 miles of space and 1 hour of time, space over time. But matter is also a kind of motion. Energy is kind of motion. Force is a kind of motion. And they all have their signature in time and space, a fraction, with space or time as the numerator, time or space as the denominator. So matter, for example, is time to the third over space to the third. Energy is time over space. Charge is also time over space, but the electron is space, and current is space over time. And so Larson gets kind of fouled up in his units last chapter, and we'll see where he goes from here with these units. So F equals Q, capital Q, Q prime, capital Q prime, over D squared. That expresses the electrostatic force. This equation is set up on an equivalent basis within a numerical coefficient. That is, the numerical value of the charge Q is defined by the equation itself. It would seem, therefore, that when the other quantities in the equation, force F and distance D, are expressed in terms of the CGS equivalents of the natural units, Q should likewise take the CGS value of the appropriate natural unit. And this comes from his discrete unit postulate. Everything is in discrete units, so there is a discrete unit of motion, there's a discrete unit of speed, there's a discrete unit of energy, there's a discrete unit of matter, and so on. And, they basically come from plugging in one unit of space, like, for example, with speed, 1 unit of space per 1 unit of time. And Larson's unit of space is approximately 2 millionths of an inch. His unit of time is 1.52 times 10 to the minus 16 seconds. And then when you equate that, the actual unit of speed is the speed of light. And he derives his other units like that. So he says Q should likewise take the CGS value of the appropriate natural unit, but the dimensions of charge are T over S, and the natural unit of T over S in CGS units is 3.33 times 10 to the minus 11 seconds per centimeter, which you get by taking the natural unit of time and dividing it by the natural unit of space. So seconds per centimeter, 3.33 times 10 to the minus 11th, whereas the experimental unit of charge has the numerical value of 4.80 times 10 to the minus 10. In conventional physics, there is no problem here, as the unit of charge is regarded as an independent quantity. But in the context of the theory of the universe of motion, where all physical quantities are expressed in terms of space and time only, it has been a puzzle that we have only recently been able to solve. One of the new items of information that was derived from the most recent analysis of the gravitational equation and incorporated into the primary force equation is that the individual force equations deal with only one force, motion. Motion is in parentheses there. The force apparently exerted by charge A on charge B and the force apparently exerted by charge B on charge A are not separate entities. As they appear to be, they are merely different aspects of the same force. The reasons for this conclusion were explained in the gravitational discussion. And this kind of stems from this idea of scalar motion, where, say, if you have the inward motion of that balloon, all of the dots are moving toward each other. If you arbitrarily decided that one of those dots is motionless, so you basically came up with a reference point of one of the dots and you define that to be motionless, then you would find that it appears as if all of the other dots are moving toward that dot, and that there is an actual force field surrounding that first dot that is attracting these other dots. And so that's why Larson uses the term apparently. It appears as if there is a force there, but there isn't. All of the dots are pursuing their own course, and they all are moving inward toward all other dots. There is no force, but it appears that there is, and mathematically it behaves as if there were. Okay, so a second point also derived from the gravitational study reported in chapter 14, although it could have been arrived at independently, is that there is a missing term in the usual statement of each of the force equations. This term, identified as 1 over s times the quantity s over t to the n minus 1 in the primary force equation, must be supplied in order to balance the equation. In the gravitational equation, it is an acceleration term. In the Coulomb equation, it is reciprocal space, 1 over s. Larson's got me lost there. I'm not sure what he's doing. It sounds like he's fudging the numbers, though, to me. I mean, I don't think he's doing it on purpose, but I think he's convinced himself that this is the right way to go, but I don't think that it is, because it sounds like a fudge factor. But if somebody could explain that to me, then I would be more apt to delve into it a little bit further to try to figure out what he's talking about there. But I've never figured that out. Okay, here, and again, that's how you have to approach the reciprocal system. There's a whole lot of stuff that you're not going to understand, And if you just reject it out of hand and put the book down, then you won't gain any of the benefits of the reciprocal system. Many, many, many times throughout my studying of the reciprocal system, I've been nonplussed about some aspect of it, and like, where's he getting that from? But then later on in my studies, he will answer my question, and it will be satisfying because I'm like, oh, I see what he's talking about now. So you can't just give up on somebody because they say a couple things that you disagree with or that you don't understand the logic behind. Larson is articulating a theory of everything, and he has to provide a new language, new concepts, new ways of thinking, and sometimes those things are hard to articulate. And so he might not always be using the optimal language to articulate these things, because he's having to do this on the fly, on his own, without, the benefit of, time-tested, communication, channels. Okay, so here we encounter a difference between the two equations that we have been examining. In the gravitational equation, the unit of mass is defined independently of the equation. In the Coulomb equation, however, the unit of charge is defined by the equation. Consequently, any term that is omitted from the statement of the equation is automatically combined with the charge, instead of having to be introduced separately, as was necessary in the case of the acceleration term of the gravitational equation. The quantity 1 over s, which, as we have seen, is required for a dimensional balance, therefore becomes a component of the quantity that is called charge in the statement of the equation. That quantity is actually t over s, the true dimensions of charge, multiplied by 1 over s, the omitted term, which produces t over s squared, which are the signature of force, the time-space signature of force. The same considerations apply to the size of the unit of this quantity. Since the charge is not defined independently of the equation, the fact that there is only one force involved means that the expression Q prime, is actually q to the 1/2 times q prime to the 1/2. So we're using the square root instead. And it follows that unless some structural factor, as previously defined, enters into the Coulomb relation, the value of the natural unit of Q derived from that relation should be the second power of the natural unit of T over S squared. In carrying out the calculation, we find that a factor of 3 does enter into the equation. This probably has the same origin as the factors of the same size that apply to a number of the basic equations examined in Volume 1. Which is his book called Nothing But Motion, which is on atomic physics primarily. And it no doubt has a dimensional significance, although a full explanation is not yet available. So this all kind of leads me to doubt all this more, but continuing on, the natural unit of T over S squared, as determined in Volume 1, is 7.31 times 10 to the minus 6 seconds per centimeter squared. On the basis of the findings outlined in the foregoing paragraphs, the value of the natural unit of charge, therefore, is Q equals 3 times 7.31 6 times 10 to the minus 6, the quantity squared, which equals 4.81 times 10 to the minus 10 ESU. And that is very close to the value that he was saying that is the natural unit up here a page or two ago, 4.80 times 10 to the minus 10. He says there is a small difference, a factor of 1.0032, between this value and that previously calculated from the Faraday constant. Like the similar deviation between the values for the gravitational constant, this difference in the values of the unit of charge is within the range of the secondary mass effects and will probably be accounted for when a systematic study of the secondary mass relations is undertaken. And I find all that to be fairly fishy also. It's kind of like he juggled the numbers around until he was able to arrive at some kind of expression that got very close to the value that he's looking for. And then he explains it away by saying that it's part of the secondary mass. The secondary mass is a very small fraction that is not taken into account with the primary mass, and it comes from, I believe it comes from like electrons in the matter and other subatomic particles that weigh like a fraction of a unit of mass. I'll get back to you on that secondary mass. I'm about to read an article about that, so maybe today I'll read that to kind of recall what exactly he's talking about. But I find it very unconvincing, but that doesn't mean that it's not right. So I just keep going on, and the equivalence of the scalar motions A, B, and BA, which plays an important part in the force relations, is also responsible for the existence of a unique feature of static electricity, the induction of charges. One of the basic characteristics of scalar motion resulting from this equivalence is that it is indifferent to location in the reference system. From the vectorial standpoint, locations are very significant. A vectorial motion originating at location A and proceeding in the direction AB is specifically defined in the reference system and is sharply distinguished from a similar motion originating at location B and proceeding in the direction BA. But since a scalar motion has magnitude only, a scalar motion of atom A toward atom B is simply a decrease in the distance between A and B. As such, it cannot be distinguished from a similar motion of B toward A. Both of these motions have the same magnitude, and neither has any other property. Of course, the scalar motion plus the coupling to the reference system does have a specific location in that system. So that's the key point about scalar motion, is that the direction is not a property of the motion. It is a property of the reference system that you define. And so once you choose one of those dots to be your reference point, then you can start measuring the directions. Prior to that, you just have magnitude and a generalized direction being in or out. But once you decide on a reference point, then you have the direction. So the direction is related to the reference system, not the scalar motion. So scalar motion plus the coupling to the reference system does have a specific location in that system, a specific reference point, and a specific direction. But the coupling is independent of the motion. The factors that determine its nature are not necessarily constant. Hence, the motion AB does not necessarily continue on the AB basis. A change in the coupling may convert it to BA, or it may alternate between the two. Okay, we're going to do one more paragraph here. The rotational component of the scalar motion of a charged atom always maintains the same relation to an atom at another location. Half of the elements of that rotational motion are approaching the second atom, while the other half are receding in equivalent directions and at equivalent speeds. But this is not true of the rotational vibration that constitutes a charge. In this case, the relation of the motion charge to the distant atom is continually changing. That is, the relative motion of the two atoms has the same vibratory character as the charge itself. As has been stated, a scalar motion A, such as a charge, toward or away from atom B, is indistinguishable from a similar motion of B toward or away from A. The representation of this motion in the spatial reference system can therefore take either form. Okay, that kind of went over my head too. I might have to go back and look at that again. We might start up with that again when we start this chapter again tomorrow. But that will do it for today. Thanks for tuning in, and just keep keep plugging away on this. Be okay with not being completely clear about everything, and just try to give him a hearing. This is a generalized theory, so we're not specifically looking at the chemistry of this for the sake of the chemistry. We're looking at it to get the concepts and to get the methodology from Larson so that we can apply his theory to other subjects as well, the same way he has. We've looked at books on metaphysics, religion, philosophy, biology, also psychology, economics we'll be looking at, and so on. Okay, thank you.